Welcome all. In this video, we will discuss the condition under which a polynomial can be solved by radicals and how polynomials of degree n greater equal 5 are not soluble by radicals. So the very first thing, the condition under which a polynomial is solved by radicals. So let's have a look. So we have a theorem. It says that the polynomial f of x can be solved by radicals if and only if its Galois group is a soluble group. If and only if its Galois group is a soluble group. So before we begin the proof, let's try to understand the idea of soluble group. So let's first of all discuss what is meaning of soluble group. So group G which has a soluble series is called as soluble group, right? What do you mean by soluble series? So for example, suppose for a given group G, we can find a series of subgroups that is single identity that is equal to G naught, say, that is contained in G1, that is subgroup of G2, and so on, subgroup of say finally GS that is equal to G, where each factor group, we can say G1 upon G naught, say G2 upon G1, and so on, say GS upon GS minus 1, are all abelian. Right? So this series is called as soluble series, and a group G which has soluble series is called as soluble group. So now we are in a position to prove our theorem. So let's go for a proof now. So firstly, suppose that f of x can be solved by radicals. So firstly, suppose that f of x can be solved by radicals, right? So by definition of soluble polynomial by radicals, we know that if polynomial is said to be soluble if each of its root can be solved by radicals. So this implies thus every root of f of x can be solved by radicals. Thus every root of f of x can be solved by radicals, right? That means each and every root is contained in the root extension. Okay, so each root is contained in a root extension which is Galois, and its every subextension is cyclic. Its every subextension is cyclic, right? Which is nothing but the result that we have proved in the previous video. We can have a look at the result here, that alpha is contained in root extension k, then alpha is contained in root extension which is Galois, and each subextension is cyclic. So we have used that result here. Okay, now if this is the case, then we'll take the composite of all these root extensions. So composite of all these root extensions will again a root extension, and it will be Galois, and every sub extension will be cyclic. So clearly I can mention here clearly, composite of all these root extensions, composite of all these extensions, because for every root there is a root extension. So composite of all these extensions is again an extension of same form. Of same form means it is again Galois extension, and every sub extension is cyclic. Okay, so now let us assume that we have such extension, root extension, composite of all these extensions is k, and suppose we are taken a series of subfields. Okay, so definitely we can find the Galois groups corresponding to each and every subfield, because we have seen in the fundamental theorem of Galois theory that there is correspondence between a field K and between subgroups of Galois group, right? So subfields of K are associated with subgroups of Galois group, and subgroups of Galois group are associated with subfields of K. So in the same manner, we can find each and every subfield which is present in this series of extensions. We can find Galois group on each and every field involved in the series of extensions. So let me just first of all assume that extension. So let say f that is equal to k naught, that is contained in k1, that is contained in k2, contained in so on, contained in ki, contained in ki plus 1, contained in so on, ks equal to k be the composite. Okay, say this is a composite of all extensions, and this is again the same form. So k is Galois extension and every sub extension is cyclic extension. Okay, now we know that as per the Galois theory, fundamental theorem, if k naught is contained in k1, then fixed field of k1 is contained in k fixed field of k naught, right? So likewise we can find for example, say k naught has a fixed field, say g naught, then this is equal to g. It contains fixed field of k1, subgroup fixing k1, say that is g1, that contains g2. Okay, where g2 is a subgroup of Galois group corresponding to subfield k2. Okay, and so on. We can find this is gi contains gi plus 1. Okay, and so on, that contains finally gs. But the only subgroup of Galois group which fixes complete field k is singleton identity. So we get this series for this particular given root extension. Now we can easily find that each of these sub extension is cyclic, so corresponding subgroups or say quotient groups will be Galois groups. So here Galois group of ki plus 1 over ki is equal to gi upon gi plus 1. This is again a fundamental theorem of Galois theory, because we know that if f is contained in E is contained in K is Galois over F. So degree of extension of K over is a coordinate of H, where H is the E is the fixed field of H is a subgroup of G fixing E, and Galois group of E over is nothing but G by H. Okay, that is index group, factor group of H in G. So that's why index of H in G is the degree of extension of E over F, and its corresponding Galois group is G by H. So we have used the same idea, because extension is Galois, this is your sub extension, Ki plus 1 is extension of Ki. So corresponding Galois group will be Gi upon Gi plus 1. Okay, so this is, but this subgroups Galois group is going to be solvable, because each of these sub extension is cyclic, so its corresponding Galois group is also cyclic, and that's why that is abelian. Cyclic group is abelian, so this implies gi upon gi plus 1 is abelian. So we found a soluble series for G. Okay, because each factor group is abelian. So by using definition of soluble group, we can easily mention that this particular group is soluble. So this implies G is soluble, right? Now G is soluble, but finally we can mention one point here, that suppose this is composite K, but the point is that the splitting field of f of x, because we are interested in f of x, so suppose splitting field of f of x is m, so splitting field of f of x is contained in K. Okay, because K is the composite of all Galois extensions, all the root extensions, okay, for each and every root. So splitting field of f of x is contained in K. Now splitting field of f of x, splitting field of f of x is contained in K, right? So I can say that suppose f is a base field, and a splitting field of f of x is suppose m, and m is contained in K, because K is composite of all these extensions. Okay, now I'm interested in what is Galois group of this, because f of x is, we can only say that Galois group is soluble if polynomial is soluble by radicals, if and only Galois group is soluble. So here I'm interested in identifying what is the Galois group of M over F. But Galois group of M over F, okay, Galois group of M over F is nothing but quotient of Galois group of K over F, because as I mentioned here, because K is Galois extension of F, so Galois group of K over F is G by H, where G is a Galois group of K. So G is a Galois group of K. Okay, so that's why Galois group of E over F is index of G, quotient of G. Okay, so definitely using that idea, here Galois group of M over F is quotient of Galois group of K, but Galois group of K is G, and we just proved that it is soluble. So Galois group of F of X is gonna be quotient of soluble group. So Galois group of F of X is quotient of soluble group, and quotient of soluble group is soluble, hence soluble, hence soluble. So Galois group is soluble. Now let's move to the converse part. Conversely, suppose that Galois group of F of X is soluble. Galois group of F of X is soluble. So my simple claim is that F of X can be solved by radicals. F of X can be solved by radicals. Okay, now the first thing is that Galois group is soluble, right? So assume that K is a splitting field of F of X. Assume that K is a splitting field of F of X. Okay, now what can we do? We can take the fixed fields of subgroups, because Galois group is soluble, so definitely Galois group has a series of subgroups. Okay, so Galois group is soluble, so it has a series of subgroups where each factor group, corresponding factor group, is abelian. So we can find subfields corresponding to each and every subgroup involved in that series. Okay, so we can take the fixed fields of the subgroups involved in that series. Okay, because Galois group is soluble, so it has soluble series, and we can take subgroups, okay, in Galois group soluble series, and we can find the corresponding fixed fields, and if we find the corresponding fixed fields, we can find a chain. Okay, so that chain will look like this: F is equal to K naught. K naught is a fixed field of whole group G. Okay, it is contained in fixed field K1, which is gonna be the fixed field of subgroup, say, just left to the G. So for example, suppose GS equal to G, then GS minus 1. So its fixed field is gonna be K1, and likewise we will find the fixed fields of all. So that is contained in Ki, contained in Ki plus 1, contained in so on, contained in Ks, that is equal to K. So K is the fixed field of singleton identity, because identity fixes each and every element of field. So K is equal to K. So we get this chain of fixed fields, okay, where each and every corresponding sub extension is cyclic extension, because we know that group is soluble, so every corresponding factor group is gonna be cyclic. So where Ki plus 1 upon Ki is cyclic. Okay, now what I will do, I will take f dash. What f dash is? F dash is nothing but, see, k1 is extension of k naught, so it is of degree n1. Suppose it is of degree n1. Let's try to say that it is of degree n1. Then k1 is extension of k2, that could be degree of n2. So on ki plus 1 is extension of ki, so suppose that extension is of degree ni plus 1, and so on. Okay, finally ns. So when we will find the splitting field, we have to consider all the n1th roots of unity, n2th roots of unity, ni plus 1th roots of unity, nth root of unity, to find all the roots of polynomial f of x. So what is f of What is f dash? So f dash will be assumed to be cyclotomic field. Let f dash be cyclotomic field over f of all roots of unity of order ni, where I is equal to 0, 1 up to s minus 1. Okay, and we'll find composite of this field f dash with the subfields contained in this extension series. So we will have a new series now. Okay, so new series will be f is contained in f dash, right? F dash is nothing but it's composite with k naught because k naught is f. So f dash f is gonna be new starting field. Okay, and then it is contained in f dash k1, then it is contained in so on, it is contained in f dash ki, that is contained in f dash ki plus 1, so on, that is contained in f dash k, right? So this is our final field. Now the point is that since these extensions are sub-extensions are cyclic, these sub-extensions are also cyclic. Okay, and we have all the roots of unity in base field. So definitely f dash k contains all the roots of polynomial f of x. Okay, and it is a root extension. So it means clearly that each of the roots of f of x is contained in root extension f dash k. Okay, that's why it can be solved by radicals, because that is a condition for root to be solved by radical, that this should be contained in root extension. So f dash k is a root extension, and all the roots of unity are here. All the roots of our unity are in f dash. Okay, f is contained in f dash, roots of unity are present here. Okay, so all the roots of polynomial f of x will be here in root extension f dash k. So that's why each root is soluble by radical. That's why f of x is also solved by radicals. So we'll just mention that point here. Since every root of f of x is contained in root extension f dash k, root extension f dash k, comma, f of x can be solved by radicals. F of x can be solved by radicals. That's it. So this is the theorem that polynomial can be solved by radicals if and only if its Galois group is soluble group. So now we will use this idea to identify why polynomials of degree greater or equal to 5 are not solved by radicals. So we have a corollary. Corollary is that the general equation of degree n greater or equal 5 cannot be solved by radicals. Cannot be solved by radicals. And point is quite clear. Proof is simple, because their Galois group is not soluble. Because see, the point is that for n greater or equal to 5, the group Sn is not soluble, right? And that's why Galois group is gonna be subgroup of Sn. Okay, so Sn is not soluble, so that's why definitely the polynomial is not soluble by radicals. Okay, and there is also another reason why Sn is not soluble, because see, for proof, for n greater or equal to 5, Sn is not soluble. Sn is not soluble because its idea is quite clear. Sn raised to 0 is Sn commutator. Okay, then Sn1 means first commutator of Sn is An, but An is non-abelian. Okay, so that's why Sn raised to double dash, that is second commutator of Sn, is going to be An itself, because it is a simple group and it is non-abelian. So that's why this commutator series will not end at identity. So that's why Sn is not soluble for n greater or equal to 5. Okay, so that's why the general equation of degree n greater or equal to 5 cannot be solved by radicals. Okay, so that's the idea. Now we will use this idea for one illustration. So we'll take one polynomial. We will take f of x equal to x raised to 5 minus 6x plus 3 belonging to qx, and we'll show that this polynomial cannot be solved by radicals. The first thing is that this polynomial is irreducible. This polynomial is irreducible because of Isington criteria, because it satisfies Isington criteria for p equal to 3. Because 3 divides constants, 3 divides coefficient of x. Okay, 3 doesn't divide leading coefficient, and 3 square, that's 9, doesn't divide constant term. So that's why this polynomial is irreducible. So first thing is that this polynomial is irreducible by Isington criteria for p equal to 3. Okay, the second thing is that splitting field of this polynomial, okay, will have a degree that is divisible by 5. Point is quite clear, because whenever you try to find splitting field, it's gonna be filled with extension, degree of extension 5 or multiple of 5. Okay, so the Galois group is therefore a subgroup of S5. So the next point is that Galois group of f of x, Galois group of f of x is a subgroup of S5 divisible by 5, divisible by 5, subgroup of S5 of order divisible by 5, to be more precise, right? So definitely the only elements in S5 of order 5 are 5 cycles. Okay, so G contains a 5 cycle. So but only elements of order 5 in S5 are 5 cycles. Okay, so G contains 5 cycles. So Galois group of f of x contains 5 cycles. Okay, now we will try to identify the roots of this polynomial so that we can find Galois group, the elements of G, Galois group of this polynomial. So that's why we need the roots. The roots will give a clear idea what could be the automorphisms. So now we can find that if I put minus 2, then f of minus 2 is minus 17, then f of 0 is 3, f of 1 is minus 2, and f of 2 is 23. That's quite easy to understand. So definitely if we'll try to find a graph of this polynomial, then f of minus 2 is negative, right, somewhere, then f of 0 is positive. Okay, so it is somewhere here, and then f of 1 is minus 2, so f of 1 is minus 2, again negative, and then f of 2 is 23, again positive, so it is positive. So when you will try to find a graph of this polynomial, this graph will intersect real line, that is x equal to x-axis, okay, at 3 points. So definitely it has at least 3 real roots. Okay, so that's why it has 3 real roots. So f of x, next point is f of x has at least 3 real roots. Okay, but point is that f of x has only 3 real roots. Now reason is that f of x has degree 5, right? Now what will happen, suppose, for example, suppose f of x has 4 real roots, then f dash of x means its derivative. Derivative of f of x is simple, that is 5x raised to 4 minus 6. It should have at least 3 real roots, then it should have, then f dash of x should have at least 3 real roots. But that is not possible, that is not exactly not possible, because 5x raised to minus 6 equal to 0, so x raised to 4 is equal to 6 upon 5, so x is 4th root of 6 upon 5, so that is 6 upon 5 raised to 1 upon 4, and into, definitely 4th root of unity are not all real, they are too complex. Okay, so that's why it does not have 3 real roots. So that's why f of x cannot have 4 real roots. So these are the only real roots of f of x. So clearly f of x has only 3 real roots. See, if I'll try to find out roots of this polynomial, then 5x raised to 4 minus 6 equal to 0, so x raised to 4 is 6 upon 5, right? So x equal to 6 upon 5 raised to 1 upon 4 into 4th roots of unity, but 4th roots of unity are 1 minus 1 I minus I, so definitely we will have rho equal to say 1 minus 1 I minus I. So it has two complex roots, so it cannot have three real roots. So that is the reason that f of x has exactly three real roots. Okay, three real roots. Okay, so finally, by fundamental theorem of algebra, f of x has five roots, three roots are real. So f of x has five roots, right? By fundamental theorem of algebra, out of which three are real and two are complex. Okay, now when you try to find automorphisms of this polynomial, okay, when you find automorphisms of splitting field of this polynomial, then definitely find that all the roots are real. So two complex root will map to each other. So there is one automorphism which maps one complex root to other complex root because they are conjugates of each other. Okay, so that automorphism will fix other real roots, because suppose tau is some automorphism, three roots are real, so three roots will be fixed by tau. Okay, tau will only interchange these two complex roots, so tau will be a two cycle. Okay, so tau which interchanges two complex roots, is two cycle. Okay, so we just establish fact that G contains a phi cycle because order of Galois group is is subgroup of S phi, and it is divisible by 5. Okay, of order divisible by 5. So it contains phi cycle. Now it contains two cycle. So combination of phi cycle and two cycle gives you S5. Okay, so G equal to S5 because G contains phi cycle, two cycle, and if it will contain phi cycle, two cycle, it will be generator of whole S5. So G equal to S5. S5 is not soluble, so that's why this polynomial is not soluble by radicals. So that's the idea, that this polynomial is not solved by radicals. But before concluding this lecture, let's go to example where a polynomial is soluble by radicals. So for that, I will take a f of x equal to x cube minus 2. Okay, what are the roots of this polynomial? So roots of this polynomial are quite simple. Roots are 2 raised to 1 upon 3, then 2 raised to 1 upon 3 omega, 2 raised to 1 upon 3 omega square, where omega is a cube root of unity. Okay, so omega equal to minus 1 plus I root 3 upon 2 because omega is a cube root of unity. Now, next thing is that if we'll try to find automorphisms of this particular polynomial, okay, f of x equal to x cube minus 2, so its splitting field is gonna be q 2 raised to 1 upon 3 and omega. These two should be attached. And if you try to find automorphisms of this splitting field over q, that is, you're trying to find the Galois group of f of x, then any automorphism can be defined by image of 2 raised to 1 upon 3 and omega. But now we have different possibilities. So we have 2 raised to 1 upon 3 and we have omega. Okay, so what will happen? There will be various in total 6 automorphisms. So how they can be defined? Say first is 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3. Okay, 2 raised to 1 upon 3 can map to 2 raised to 1 upon omega. 2 raised to 1 upon 3 can map to 2 raised to 1 upon 3 omega square, and omega can map to omega, omega can map to omega square. Okay, so point is that roots of this polynomial are 2 raised to 1 upon 3, 2 raised to 1 upon 3 omega, and 2 raised to 1 upon 3 omega square. Whereas omega is a root of polynomial x square plus x plus 1, because x cube it is a cube root of unity, so it is root of x cube minus 1 actually, but x cube minus 1 can be factored as x minus 1 into x square plus x plus 1. So omega is a root of x square plus x plus 1, so omega can map to either omega or omega square. So 2 raised to 1 upon 3 can map to one of these roots, omega can map to one of these roots. Based on this, there are 6 possibilities. So 2 raised to 1 upon 3 can map to 2 raised to 1 upon 3, omega can map to omega, it can map to 2 raised to 1 upon 3 omega, omega maps to omega, it can map to 2 raised to 1 upon 3 omega square, omega can map to omega, then 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3, omega maps to omega square, 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3 omega, omega maps to omega square, 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3 omega square, and omega maps to omega square. So these are the 6 automorphisms which can be identified. Okay, so what I will do, I will first of all write this automorphism where 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3 omega. Omega is fixed. Let me call this as sigma, this automorphism, and where 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3 omega maps to omega square. Let me call that as sigma, or let me call this as tau. Okay, let's have some other symbol. So let me call that as a tau. So this is sigma and tau. Now we will try to identify what are the other automorphisms are. This is clearly identity. Okay, this is gonna be sigma square. Okay, because omega is fixed, so this is gonna be sigma square. Now we will try to identify what are these automorphisms. Okay, now let's try to identify the remaining two automorphisms. So here 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3 omega, and omega maps to omega square. So let's try to identify what is this. So if we take composite of tau and sigma square, then we will get tau sigma square. So it will be tau sigma square of 2 raised to 1 upon 3, that is tau, or first of all let's try to identify what is tau sigma, then the remaining map will be tau sigma square. Okay, so that will be quite easy for us. So tau sigma of 2 raised to 1 upon tau of sigma of 2 raised to 1 upon 3, but 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3 omega, so tau of 2 raised to 1 upon 3 omega. So this is tau is automorphism, so tau of 2 raised to 1 upon 3 into tau of omega, but tau of 2 raised to 1 upon 3 is 2 raised to 1 upon 3 omega, and tau of omega is omega, so this is omega square, right? So tau sigma of 2 raised to 1 upon 3 is tau of sigma of 2 raised to 1 upon 3, that is tau of 2 raised to 1 upon 3 omega, but tau of 2 raised to 1 upon 3 omega is tau of 2 raised to 1 upon 3 into tau of omega, because tau is automorphism. 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3, 2 raised to 1 upon 3 maps to 2 raised to 1 upon 3, right? And omega maps to omega square, because tau of 2 raised to 1 upon 3 is 2 raised to 1 upon 3, and tau of omega is omega square, so 2 raised to 1 upon 3 omega square. So this is your tau sigma, right? This is your tau sigma, and remaining map will be tau sigma square. So if you want to identify, you can identify tau sigma square of 2 raised to 1 upon 3, so that is tau of sigma square of 2 raised to 1 upon 3, but tau of 2 raised to 1 upon 3 sigma square of 2 raised to 1 upon 3 is 2 raised to 1 upon 3 omega square. Okay, so this is equal to tau of 2 raised to 1 upon 3. Tau of 2 raised to 1 upon 3 is 2 raised to 1 upon 3. Tau of omega square, but tau of omega square is tau of omega into tau of omega. Okay, so tau of omega is omega square. So omega square into omega square, that is omega raised to 4. But omega raised to 4 is omega because omega is square root of unity. So omega cube equal to 1. So 2 raised to 1 upon 3 omega. So simply this is tau sigma square, right? So this is your map. Now if you try to identify tau sigma, let's try to identify what is sigma tau. So sigma tau of 2 raised to 1 upon 3 is a sigma of tau of 2 raised to 1 upon 3. That is a sigma of tau of 2 raised to 1 upon 3 is 2 raised to 1 upon 3. Okay, so sigma of 2 raised to 1 upon 3, that is a 2 raised to 1 upon 3 omega. Okay, and sigma tau of omega is sigma tau of omega is sigma of tau of omega. Tau of omega is omega square, so sigma of omega square. So sigma of omega into sigma of omega, that is omega square. Okay, so 2 raised to 1 upon 3 omega and omega square. So this is tau sigma square. So this implies sigma tau is equal to tau sigma square. So definitely this automorphism group is of order 6. It is generated by sigma and tau, where sigma tau equal to tau sigma square. So definitely it is symmetric group S3. So thus Galois group of x cube minus 2 is S3, right? And S3 is soluble because if you find commutators of S3, S3 raised to 0 is S3, then S3 raised to 1 this A3, then S3 raised to 2. Now A3 is of order 3, right? Every group of order less than 5 equal to 5 is abelian. So when a group is abelian, its commutator is singleton identity. So second commutator of S3 is identity. So that's why S3 is soluble group. So S3 is soluble. So this implies x cube minus 2 is soluble by radicals. Soluble by radicals as per the theorem. Okay, so in this way we can find whether a given polynomial is soluble by radicals or it is not soluble by radicals. So in this particular video we observed the condition under which a polynomial is soluble by radicals. We took a glimpse of the corollary that general equation of degree n greater equal to 5 cannot be solved by radicals, and we took two examples of polynomials where one was soluble by radicals, where other was not soluble by radicals. So with this I take stop here in this lecture. Thank you.